IUPAC rules. Now, there's always rules, right? This is chemistry, so there's rules. Now, when you're going to name an alkene, first of all, does it have a double bond? If it does, it's an alkene. So you find the longest continuous chain of carbons. Sounds very familiar to alkane naming, but now you have to make sure the longest continuous chain contains the double bond. So that means if you can count two different chains, one contains a double bond, one does not, you always pick the one that does, even if it's shorter. You always pick the longest continuous chain that contains the double bond. You change the suffix of the root name from an ane to an ene. So for example, if you have say a butane, and then now you have a butane with a double bond, it's not called butane anymore, it's called butene. Butene. Number the carbons in the chain so that the double bond has the lowest possible numbers. In other words, you start numbering closest to the double bond. The double bond always has the lower numbers. So if you can number the chain two different ways, one will give the double bond higher numbers, the other gives it lower numbers, you always pick the lower numbers. Double bonds always have low numbers. The double bond is always between carbon 1 and carbon 2 in a cyclical compound. So in cyclic compounds or ring structures, carbon 1 and 2 is always the double bond. So now let's learn how to apply IUPAC rules to naming alkenes. Now, unfortunately, or fortunately as the case may be, depending on your point of view, there's a new way to do it. IUPAC has come up with another way to do it that is probably less ambiguous, but both ways are still out there. You can still find the old way of naming things online, find it in older books, it's there. So I'm going to show you both ways. It's not that big of a deal really, because the only thing that's really different is the location of a number. The number that tells you where the double bond is actually is what's changed. It's just changed locations in the name. It's not a big deal. So now, we want to name this bad boy right here. So we have to number the longest continuous carbon chain. So you can number it from this side, 1, 2, 3, or 4, or you can go from the other side, 1, 2, 3, or 4. Now, you have to pick whichever numbering system gives the double bond the lower number. So obviously, the red numbers give it the 1. So the double bond would start at carbon 1 and go to carbon 2. The purple numbers start at carbon 3 and go to carbon 4. So obviously, the purple numbers are not the right ones because they're giving you a higher number. So let's get rid of the offending numbers. Now, this has 4 carbons, so it's a bute. It's a bute something. It has a double bond, so it's a butene. And the double bond starts at carbon 1, so it's a 1-butene. That's the old way of doing it. This is the old way. The old way, or the antiquated way, or the antique way, however you want to say it. The new way would do it like this. But-1-ene. And I'm guessing they did it for consistency because in naming, say there was a chlorine here, you would say 1-chloro. The 1 comes right in front of the substituent, or right in front of the thing you're talking about. So it's 2-methyl, 3-chloro, 1-bromo. So here they put the 1 right in front of the ene. So 1 goes right in front of the double bond. I guess that's why they did it. I really don't know why they did it. I just know this is how you apply the rule. Okay? So keep that in mind. There's the old way in red and the new way in blue. Let's do this one. 1, 2, 3, 4. 1, 2, 3, 4. So this particular one, no matter which way you number it, you're always going to get the number 2. So from the red numbers, from carbon 2 to carbon 3 is your double bond, so it will be 2. From the purple numbers, again, carbon 2 to 3. So the purple numbers and the red numbers give you the same number, value for the carbon that starts the double bond. So it doesn't matter which one you pick. I'll pick the red. The old way, 2-butene. The new way, but-2-ene. So I like the new way better, the blue letters, but I teach both because I want to make sure that you're not ever in a situation on an exam or something where you're seeing the old way of doing it and you're confused by it. And I don't think it's that big of a deal, really. All right, a couple more simple examples. So let's start. Now, how do I do it? I don't normally number from one side to the other. I just do that for students to kind of show you the point. I always just find the double bond, and I start numbering at the carbon closest to it. So this is my longest continuous chain. This is the carbon that's closest to the double bond, the terminal carbon that's close to the double bond. So this is carbon number 1, 2, 3, 4, and 5. So it's a pentene. So this is 1-pentene, or the new way, pent 1-ene. The bottom one, this is a 1, 2, 3, 4, and 5. So this is 2-pentene. Oops. Or the new way, pent 2-ene. And that's how you do it. I don't think this is very difficult. I think if you can do alkanes, it's just a small extension from alkenes. You just have to tell the reader where the double bond is. And you do that by just telling them where in the chain it starts. Ring nomenclature. Now, rings are not hard either. Let's just do it. The rule is this. It's very simple, that the double bond always gets the number 1 and 2. The double bond always starts the numbering. So for this example here, we have a double bond here, but we don't have any substituents. So we don't have to say 1-hexene. If we just say cyclohexene, the reader will assume that the double bond starts at carbon 1, because it doesn't matter if we draw the cyclohexene like this or we draw cyclohexene like this. It doesn't matter. It's still cyclohexene. It's still 1 cyclohexene. The 1 is assumed. So for this example, you can just write cyclohexene. If it was a cyclopentene or cyclobutene, you could just write the words, because there's only the double bond. When you have substituents on the ring is when you have to start numbering. So remember, carbon 1 and carbon 2 always have the double bond. Always. So in this example, there's a choice we have to make. Do we start numbering carbon number 1 here, number 2 there, or is it number 1 here and 2 there? Going back to the alkane nomenclature, I think everyone will agree the red numbers are correct. Why? Because not only does it give the double bond, the 1 and the 2, it also gives the methyl, the 1. So it's 1-methyl cyclohexene, not 2-methyl. So let's write that out. 1-methyl not, oops, sorry. Let me write that in red to be consistent with the letters here. Sorry about that. 1-methyl cyclohexene. Notice you don't have to say 1-ene, cyclohex 1-ene or anything like that, because the 1 is assumed to be on the double bond. It's not this. So 2-methyl so let's put a big X over there. No, it's not that one. Why not? Because I could have numbered the carbons in a way that gave a methyl group a lower number. You always do that. You always want to have the substituents on the lower number. So when you can number the double bond from here to here or from here to there, number it the way that gives the substituents the lower number. Okay? But carbon 1 and 2 always have to be the double bond in the ring. A couple more examples. So here we have another ring system. I could name it like this, 1, 2, 3, or I could go 1, 2, 3. There's a few other ways you could number it, but the only way that's correct so far or ever is the red numbers, because the red numbers give this substituent and this substituent the lowest numbers. So this one is 1, 3 dimethyl cyclohexene. That's how you number that one, because it gives the two methyl groups the lowest numbers. Okay? And also, you can't use the purple system because it doesn't give the double bond number 1 and 2. Okay? Let's try this one over here. So we could start numbering here. 1, 2, 3, 4. I guess we could go back the other way. 1, 2, 3, 4, 5. So the black letters don't seem like they're going to work out well for us because it's giving the 2 and it's giving the methyl and the ethyl higher numbers. So the red numbers are going to win. So this is going to be 4 ethyl. Oops, let me change colors. 4 dash ethyl dash 1 dash methyl cyclohexene. Now the ethyl has to go first because remember, substituents are named alphabetically. Doesn't matter that the methyl has the number 1. What matters is that ethyl E becomes before M. That's what matters. Multiple double bonds. So now what happens if we have more than one double bond in a chain? Don't let that phase you. It's not a big deal. You treat it exactly the same way you would if you had 4 or 5 methyls. It's easy. So again, you have to number the carbons so that the double bonds have the lower numbers. So this is 1, 2, 3, 4. So far, so good. But now there's 2 double bonds. So just like if it was methyl, if there's 2 methyls, you'd say dimethyl. And alkene chemistry, you would say diene, 2 enes. 2 enes. Ene is another way of saying double bond. Diene, 2 enes. Easy enough. The old way, 1 dash 3 dash bute diene, 1,3-butadiene. The new way, you would say bute dash 1, 3 dash diene. So you see, the only thing that's different is we move this numbering system into the name. That's all the differences are really. This one, 1, 2, 3, 4, 5, and 6. So the old way, 1, 3, 5 dash hexa tri, ene. Cyclohexatriene. Now the new way, of course, would be hexa dash 1, 3, 5 dash triene. That would be the new way. And that's the basics on how you name alkenes. Now, the rest of if there's ever any other substituents, the rest of the substituents follow alkane rules. They just, you number them you put them in alphabetical order, the numbers and all that stuff. Same as alkenes. The only thing that's different here is now we're having to tell the reader or the user where the double bonds are in the chain. Cis-Trans Isomers. Now we talked a little bit about this early on in the lecture. Now we're going to talk a little bit more about it just so we can make sure everyone's on the same page with how to identify cis versus trans. So in cis and trans, you look for the carbon-carbon double bond. And on this double bond, you look for the hydrogens. Or you look for the alkyl groups. Either way, depends on how you want to do it. I personally look for hydrogens just because I find it easy. I've been doing it my whole life. Hydrogen on one carbon is going up. Hydrogen on the other carbon is going down. Now, it doesn't matter that it's up and down. What matters is that it's opposite. So we have this hydrogen on the top side of the double bond. This hydrogen's on the bottom side of the double bond. They are trans. That relationship is referred to as trans. Trans. One side, the hydrogen is going up, for example. The other side, the hydrogen is going down. This is a trans relationship. Now over here, when hydrogen's up, the other hydrogen's up. It doesn't matter that they're up. It matters that they're in the same direction. So this particular olefin is cis. That's the cis stereochemistry. Trans, hydrogen on one carbon is up, hydrogen on the other carbon is down. That's trans. What matters is that they're opposite, not that it's up and down. This one, hydrogen up, hydrogen up. Doesn't matter that it's up. It matters that it's the same direction, up. Could have been both been down, both been left, both been right, both been diagonal, left, whatever. Doesn't matter as long as it's the same direction. Now, before you start thinking that every double bond in the world has some sort of stereochemistry, they don't. Sometimes you'll get things like this. These don't have cis and trans, because if I move this hydrogen down to here and this hydrogen up to there, I get the same molecule again. So this particular olefin does not have cis and trans, just doesn't have it. In order to have cis and trans stereochemistry, you have to have one hydrogen on each carbon of the double bond. If you have more than one hydrogen on one of the carbons of the double bond, you cannot have cis and trans. That's just how it works. Unfortunately, not every double bond that has stereochemistry falls neatly into the cis-trans environment. Sometimes you have 4 different groups on a double bond, so you can't possibly use cis and trans. You can, however, use E and Z. Conningold and Prelog came up with a method of telling a reader what type of double bond orientation you have without using cis and trans for examples that don't fall into that category. So, remember the Conningold-Prelog rules. It's all about priority, right? It's all about who has the higher atomic number. So don't forget that. When the high priority groups are on the same side of the carbon-carbon double bond, that is the Z stereochemistry. Just write this down. We're going to do examples, and you'll get it. Once we do a few examples, you'll be like, oh, that's all this is? Very simple. When the high priority groups are on the opposite side of the double bond, that is the E stereochemistry. Okay? So Z means on the same side. E means on opposite side. Z on the same side. E on opposite sides. So let's do this example right here. Now what I tell students to do is I say, okay, just draw a dotted line down between the 2 carbons. And now you're going to look at the left side independent of the right side for now. So now I want to figure out which one of these 2 groups has the higher priority. Who has the higher atomic number, in other words. Bromine comes under chlorine in the periodic table, so therefore it has a higher atomic number. So bromine is priority group number 1 on the left-hand side. Chlorine is priority group 2 on the left-hand side. On the right-hand side, hydrogen has to be priority group 2 because it's always the low priority group. And methyl is priority group 1. So that's how you would name this in terms of E and Z. That's how you would name this in terms of E and Z. So this is, well, 5, 4, 3, 2. So now in this particular molecule, the high priority groups are on opposite sides. So that's E. This is an E stereochemistry because the one group and the one group are on opposite sides of the double bond. So let's put it all together. So this is a propene. So this is going to be carbon number 1, carbon number 2, carbon number 3. So we have 1 chloro, 1 bromo. All right, so we have to put all this together. So it's going to be E dash 1 dash bromo. Remember, bromo comes before chloro because bromine has a B, chlorine has a C, chloro has a C, dash 1 chloro propene. That's how you would name that particular molecule. Notice the stereochemistry of the double bond came in front. And I did my best, but this should have been italicized. I tried my best to show it as an italics, but when you're typing it, you would just type it as an italic. So what happens if we have multiple double bonds with stereochemistry that we have to talk about? Very simple. Let's first figure out if these double bonds are E or Z. Let's first figure that out. So let's draw a line like that and a line like that. So between this one and this one, the bromine has the high priority. So that's 1 and that's 2. So it's carbon versus bromine, right? So bromine wins. Here it's hydrogen versus carbon, so that's 2 and 1. So here, the high priority groups are on the same side, so that's Z. So the stereochemistry of that double bond is Z. Now let's worry about this one. Hydrogen here, and there's a hydrogen here. So that's going to be 2, and this will be 1. That's going to be 2, and this will be 1. So the double bond stereochemistry here is E, because the high priority groups are on opposite sides. So the stereochemistry there is E. So now we have to put all this together. So let's back out of this. I'm just going to back out to get rid of my drawings. And I just want to remember that that one is Z and that one is E. Oops. That's all I want to remember. I want to get rid of all the other accompanying items. All right, now that we have our E and Z stereochemistry figured out, we have to put everything together to get the name. So to do that, let's number the carbons. So we have to start numbering from the N carbon closest to the first double bond. So we can start here, 1, 2, 3, or we can start over here, 1, 2, 3, 4. So we're going to start here because that gives me the lower numbers. So let's say carbon 1, carbon 2, carbon 3, carbon 4, 5, 6, 7, 8, 9. So this is a nonene. It's got a non-diene actually. It's got 2 double bonds. So we have to tell the reader the stereochemistry of both double bonds. So open parentheses, 3Z, comma, 5E, close parentheses. Now what's this saying? This is saying at carbon 3, there's a double bond, and that double bond stereochemistry is Z. At carbon 5, there's a double bond, and the stereochemistry of that double bond is E. That's what it's saying. So 3Z, so carbon 3 double bond stereochemistry is Z. Carbon 5 double bond stereochemistry is E. How do I know it's a double bond? Just by reading this, because the only thing that has E and Z nomenclature are double bonds. Nothing else does. Now, let's continue. So that's going to be dash 3 dash bromo nana dash 3 comma 5 diene. And that's how you'd name it. So on the carbon 3 there's a bromine. It's a nana, which is 9. Nonane, 9 carbons. Diene, 3 comma 5 diene. That's the new way of doing it. All right? So that is how you would name that molecule using the new nomenclature. If you didn't get it or you don't understand it, maybe watch this part of the video again, or better yet, cover up my answer, do it yourself, and it might become more real to you. You may have to struggle with this for a minute.